Alright, so today we are going to discuss these exercises 17 through 28, and here we just have to simply differentiate the given function once. So let's see the 17th one. In this one we have to use the quotient rule. We cannot change this ratio to anything else that will be easier for us to differentiate. We just simply straight away we have to use the quotient rule. So let's see the solution. We have dy dx it's a good idea to first write this and then apply the quotient rule. Two x plus 5 divided by 3x minus 2. So what does the quotient rule say? It first says that the denominator, since it will take some space, so let me first write the denominator separately, like this. This ratio separately. So what the quotient rule says is that we have to square the denominator of the original quotient of two functions. And then you have to, in the numerator, you have to do first what? You keep the denominator as it is, and with that you multiply the derivative of the numerator. That is this 2x plus 5 minus, do not forget that in the quotient rule you have minus, unlike the product rule where you have plus. This time we will keep this one intact, and with that multiply the derivative of the denominator this time, that is 3x minus 2. Okay. So this becomes, and now we have to actually do the, here also we are differentiating, but now we have to do it on these polynomials. Okay, so this is where we will use our already known formula for differentiation. For example, you are going to use the power rule here and the constant function rule here. They are going to give you zero derivatives. Times 3x minus 2. Okay. Now first of all, by the constant multiple rule, actually you first apply the sum rule. This is equal to the derivative of 2x plus the derivative of 5. Derivative of 5 is 0 by the constant function rule or constant rule. In derivative of 2x, 2 comes outside by the constant multiple rule, and then you differentiate x with respect to x by using the power rule, which tells us that the derivative is 1. That means the derivative of this entire thing is 2 times 1 plus 0, or 2 minus similarly the derivative of this will be 3 times 0, 3 times 1 minus 0, or 3. Minus 2x plus 5 times 3. So now it equals, now I think we can write it like this. We have space now. So if you do the multiplication, you are going to get what? 6x minus 4. And do not forget that you have a minus sign. So when you multiply this polynomial by minus 3, you get minus 6x minus 15. And the denominator was this. So you see there is a cancellation. That means ultimately you are getting minus 19 divided by 3x minus 2 whole square. This is the derivative. The 18th one is similar. Let's at least see what it is. Here, instead of calling the dependent variable y, the authors have chosen to call it z. That's not a big difference, it's just another name. You still have to write dz dx, okay, or dz dx, no matter whatever you want to call it, z or z. Do not write dy dx, okay, and also if it's given as z, don't write it as y, saying that you can give it any name you want. No. If it is given as z and there is no good reason to change that name, you keep that name like that. 2x plus 1 divided by x square minus 1. Same thing, you just have to apply the quotient rule here also exactly similarly and you will get the answer. So I leave this to you. The 19th one is also similar. Here, the function itself has been given a name, g, and we also see the independent variable x. These different notations should not confuse you. These are just different ways of expressing the same thing. If one wants, one can also write y or z here. Nothing essentially will change. That is just another way of writing it. Divided by x plus 0.5. Same. Okay, so this also I leave to you. Next, the next one, however, has something different from these ones. Although it's also a ratio of two polynomials and hence is a rational function, but unlike these three exercises, here we can do some simplification first and then go for derivative. Here the function is f of t is equal to t squared minus 1, that's the numerator, and the denominator is t squared plus t minus 2. And these two polynomials can be factorized as products of linear polynomials, and after that there is a cancellation. So we first do the simplification. We note that f of t is t square minus 1 divided by t square plus t minus 2. The numerator, of course, it's very easy to factorize it. It's already in the form. So it's t plus 1 times t minus 1. The denominator, it may take some time to see what a possible factor can be. But you recall how you used to find factors of polynomials by finding some root of them. If you put t equal to 1, for example, it's very easy to see that 1 plus 1 will be 2, 2 minus 2 is 0. So 1 is a root of this polynomial, which means that t minus 1 should divide this polynomial. and it's not difficult to figure out that it's actually equal to t minus 1 times t plus 2. You can do the multiplication and see for yourself. T times t will be t square. 2t minus t will be t, and minus 1 times 2 is minus 2. So this is it. And now you can see that you can cancel this t minus 1, thus obtaining this simpler representation of that same function, which doesn't involve these quadratic things. And now you can do it as we solve the first one, but still let's just do it. Now, because it's given as f of t, now you have a choice of how you want to write the derivative. You can write df dt, or you can use the prime notation also, f prime t. Let's use the prime notation. It also means derivative, f prime t. This is nothing else but the derivative of the function with respect to t. So applying the quotient rule, I think I can write it here itself, I mean in this way. There's enough space. So we square the denominator, then we keep the denominator intact first, multiply it by the derivative of the numerator minus, then we keep the numerator intact and multiply it by the derivative of the denominator t plus 2. Now if you do the differentiation, differentiating t you will get 1, and differentiating 1 of course you get 0. Similarly, that one is also just 1. So you can see that here you are actually having t plus 2 minus t plus 1. So that is 1 divided by t plus 2 whole square. So that's the derivative. If you want, you may not go through this simplification process. You can straight away apply the quotient rule to this itself. If you want, you can do, but in this way also one can do. That won't, I'm not saying that that will be very difficult. You can do that, but sometimes going through a simplification first will save your time. Okay, so the answer is 1 over t plus 2 whole square. What is the next one? The next one is again like the others, but written in a slightly different manner. And the dependent variable also has the name v. This is 1 minus t times 1 plus t square to the power minus 1. So no need to be confused with this. You just start the solution like this. We have v equal to 1 minus t times 1 plus t square to the power minus 1. So obviously it's just this. That's it. And then you apply the quotient rule as usual. So this also I leave to you. Next, 22 is also similar. here the dependent variable has name w, and it is 2x minus 7 to the power minus 1 times x plus 5. Now this of course can be written like this. You see, the authors have knowingly put this factor first so that we get confused and we may end up writing 2x minus 7 divided by x plus 5. Don't do that mistake. The exponent minus 1 is over 2x minus 7. So, when you express it as a quotient, 2x minus 7 goes down. And then you apply the quotient rule to it to find its derivative. So, this one also is left to you. Next, 23. F of s, here the independent variable is being called s. This is square root of s minus 1 divided by square root of s plus 1. Now, there may be a temptation of trying to rationalize the denominator. You can do that if you want by multiplying and dividing by square root of s minus 1, so that the denominator becomes square root of s square minus 1 or s minus 1. However, that won't really get you rid of this square root entirely, because the numerator then will be the square of this, and when you expand that square, you will have minus 2 root s still there. Okay, so if you want to get rid of the square root completely, you cannot do that. So I think it's better to apply the quotient rule as it is, I mean straight away to this itself. Let's see what we get if we do. We have, so again here let's write the derivative as f prime s. So this is, don't write ddx or ddt s, because s is the independent variable. Minus 1 divided by root s plus 1. Okay. So as usual, first we square the denominator, then write the denominator times s again. Okay, keep this in mind. The derivative of the numerator minus the numerator times, I am running out of space, root s plus 1. Okay. And now, if you remember, what is the derivative of root s with respect to s? It is 1 divided by 2 root s. If you cannot remember how that is the case, let's just go through the details here. We have in fact already calculated this derivative. This is 1 divided by 2 root s. Actually, it is also a power rule. but we haven't really got this form of power rule yet. You can write root s as s to the power 1 over 2. Now, if you simply, in spite of not having seen this form of power rule, if you just simply go for it, the way we calculate such derivatives when the exponent is an integer. So what do? You just bring the integer down. Here also let us bring 1 over 2 down. And then you write the original power and subtract 1 from the exponent. That way, if you do the calculation, 1 over 2 minus 1 is minus 1 over 2, or 1 divided by root s. Now, you may ask me, where are we getting this from? Since we haven't really seen this form of power rule where the exponent can be a fraction, how do I know that this is correct? Well, if you actually go back to that section where we defined derivative and used the definition of derivative to calculate many derivatives and slopes of tangents, there you will see that we have in fact already found this fact, that if we differentiate root s with respect to s, then this is the answer. So from there we are getting this, although we haven't really still got the power rule in this form. That we are yet to see that, but still we at least have this. So now we can use that here. Minus 1 when differentiated, of course, will give us 0. So here you have 1 divided by 2 root s, which is coming from this one, minus root s minus 1 times, again from this one also, we are going to get just that. Now if you do it, now you just have to do simplification. So we can write this 2 and root s in the denominator. And the original denominator was already this. Root s plus 1 minus root s minus 1, or minus root s plus 1. That means root s minus root s will vanish and 1 plus 1 will be 2. Upon cancelling the 2 from the numerator and denominator, we are finally left with this. Yeah. So that is the derivative. If you encounter some such situation where you don't exactly know what the derivative is, then you have to just apply the definition, because that's where everything is coming from. No, you have to apply the limit definition of derivative. If you are still somewhat doubtful about this, you just straight away write what the derivative means. Limit h tends to 0, that thing. Square root of s plus h minus square root of s divided by h. Calculate that limit, you will see that this is the limit, which is what I am saying we already did. Okay. Next, 24, this one. It looks like we have to use the quotient rule, but we can in fact simplify the situation. 5x plus 1 divided by 2 times square root of x. There are two ways of doing this. One is to straight away use the quotient rule, and the other one is going through this simplification first. So let us see what we get if we try to simplify this. You can perhaps already see what I mean by simplifying this. Note that plus 1 divided by 2 root x. So if I do the division, in this case I can, because the denominator is quite simple. Then there is a cancellation, and after cancelling I have root x here. But when I divide 1 by this, I have this. Is it really going to help me though? This part I know will come just like that. But what about this part? This is also a power of x, x to the power minus 1 divided by 2. However, the derivative of that we haven't really found so far. So, if you really want to do the calculation like this, after simplification, there are some fireworks going on in the background, okay, because of something I don't know what. So, I cannot do anything about it. Okay, so please bear with me. The problem is with this term. This term, we don't really know exactly what to use. I mean, we do not have a formula for this. If you want to apply the quotient rule here, then there is no point in going through the simplification. You can straight away apply the quotient rule here itself. However, you can try to know this. Now there are two ways. One of them is to use the quotient rule here, which we already have said it's pointless. You can apply the quotient rule to the original function to find this derivative. The other way is to use the definition of derivative itself, limit. That also you can do, but looking at this now we realize that the simplification is not really going to give us anything useful. I think it's better to use the quotient rule straight away itself. This is how. When you start solving something now, you don't immediately know what to do. It may take some time for you to think what will work the best. Okay. So now that we know we have to use the quotient rule, so let's just do that. Actually, there is absolutely no law and order. See, not only are firecrackers banned, but at this time of night they should not go off, but still things are just like that. So, we cannot start the solution like this. Instead, we have to use the quotient rule. So you square the denominator, that will give you, let me write straight away, 4x, and then you keep the denominator intact first, and differentiate the numerator, and then you keep the numerator intact and differentiate the denominator 2 root x. So although we have root x here, but at least we know its derivative. So we do not encounter this problem with this method. So 4x. Now you know what will happen if you differentiate this. You will get 5. 5 times 1 plus 0. That 5 and this 2 will give you 10 root x minus 5x plus 1 times, from 2 root x, 2 of course comes outside, and then you differentiate root x, and we already know what the derivative is, 1 divided by 2 root x. So there will be that little cancellation there. And then, if we do further simplification, or let me just, instead of skipping steps like this, let me just write one more line. What's the harm? Times 1 divided by root x 4x. And now if I bring this root x in this entire, below this entire thing, then this gets multiplied by root x, becomes 10x minus, and here nothing will be there except 5x plus 1. Alright. So 10x minus 5x is 5x minus 1 divided by, okay, now if you use one of the two rules of exponents, you have x and root x. Root x means x to the power 1 over 2. So you add the exponents 1 and 1 over 2 and get 3 divided by 2. 3 divided by 2. So this is the derivative. At first I thought that simplification will help us, but it turned out to be a problem itself. So that was 24 and then 25. 25 is also similar, also like this. V is equal to 1 plus x minus 4 root x divided by x. So this tempts us even more to do that simplification, but again, you will have problem with 1 divided by root x here. So it's better you apply the quotient rule, or if you really want to calculate once and for all the derivative of 1 over root x for once, and then keep using it wherever it appears, that also you can do. You do the hard work once and then just keep on using your result. That also you can do. Whatever you do, you please do it. So that's the 25th one. Then 26th one. This is also similar. Here the dependent variable, however, is r, and the independent variable is being called theta. So this reminds us of polar coordinates in the plane r and theta. Here also you see already this thing is present here in this form itself, in the exercise itself, in this form, this is present. Only in place of x, here we have theta. So if you already have that thing ready for you, you can straight away use that here and use the other thing here and immediately calculate the derivative. If not, you express this entire thing as a ratio and it will simply be, you can see 1 plus theta divided by root theta, and then apply the quotient rule. Okay, so this also you do. Next, 27. Yeah, this one I will do. Here there's almost nothing in the numerator, just 1, and the denominator, however, is this. X square minus 1 times x square plus x plus 1. We just have to use the quotient rule. So let's just do that. We have dy dx equal to, okay. Now, of course, I have to write the denominator separately because it will take some space. So what do? We first square the denominator. Let me write that part separately like this. Squaring the denominator means squaring both these factors times. Then let me first write the thing and then we will decide which one vanishes, which one stays. The denominator is kept intact in the first term and we multiply that by the derivative of the numerator, which in this case is 1. So this will vanish, minus 1, which is the numerator, that we can keep intact here in the second term, and then multiply that by the derivative of the denominator. Yeah, this is going to be somewhat large. I am using the curly brackets to indicate the fact that this product has to be differentiated. And also do not forget the square bracket. So this term is going to vanish because of this 0 here. Because it will vanish, now I can write it as a ratio in the normal way. Oh, but okay, hold on. No, now also there is a little problem in writing it like that. So let me keep on using this form. So minus of this. This itself, however, is a product. So to differentiate this, there are two ways. Either you can use the product rule or you can multiply the terms first and then do differentiation. It's up to you what you want to do. Let me use the product rule. So if I use the product rule, oh, and one more thing, if you keep this minus 1 here in the numerator itself, if you want, you can write minus in the denominator also. What I am trying to say here is that you separate this minus from this entire differentiation process. No need to write any minus here. And for that, I write minus 1 there with this thing above it. So if I now use the product rule, let me first keep x square minus 1 as it is times d dx of x square plus x plus 1 plus, not minus this time, because it's the product rule, so plus. Then I keep x square plus x plus 1 unchanged and multiply that by the derivative of x square minus 1. Okay. Now what shall I get? Times. So if we do the differentiation, x square will become 2x. X will become 1 plus x square plus x plus 1 times x square will become 2x minus 1 will become 0. So this is just 2x. And then you do the multiplication, simplify the numerator, because this is the numerator after all. No? Although we are writing it separately, but this is the numerator. Simplify the numerator and then see if something gets cancelled with the denominator. So I am keeping it like this. I leave the rest to you. You do the simplification and see if anything can be simplified. But at least you do the multiplication and do the simplification in the numerator. And finally, there is this one, 28. Y is equal to x plus 1 times x plus 2 divided by x minus 1 times x minus 2. Here also there are two choices. You have to use the quotient rule, no doubt about that. There is no choice in that. But before you do so, you can, if you want, do the multiplication in the numerator and denominator. You can see that in that problem where you had t square plus 1 divided by t square, something like that was there. There you did factorization and then you saw that there are common factors which can be cancelled to simplify the situation. Here that's not the case. So if you do multiplication, then you will get a quadratic polynomial as numerator and a quadratic polynomial as denominator. You can then apply the quotient rule, or you can straight away apply the quotient rule and then you will encounter a situation like this where you will have to once differentiate this product and another time you have to differentiate this product, where you can either use the product rule or there you can do the multiplication and then differentiate. Okay, so essentially it's just it has the same form as this one, and that's why this also I am leaving to you. The more you practice these things, the easier the things will become, the more natural they will become, and the faster your process will become without making any mistakes. So that's just it. Let me end this video here itself. And tomorrow, as usual, we have our linear algebra. And since we have already completed this ongoing section, completed means we have completed the theory part. So tomorrow we will start solving problems, but not in the community section anymore. problem will be solved in a video. So see you tomorrow with that. Until then, this is me, Lucifer from A Mathematical Room. Have a nice night.